Hey everybody, this is Mr. Piercy again. We're going to be continuing on. This is our second video on infinite limits and limits at infinity. So here, after we have looked at the behavior of the functions as they approach infinity or as they approach a number using a one-sided limit, we were able to use that to justify where there was going to be, say, a vertical asymptote, a horizontal asymptote, or a slanted asymptote in the case of a top-heavy rational function. So here, we're going to be kind of recalling some prior knowledge from earlier math classes about properties of rational functions. Here, when a factor is canceled from the numerator, from the denominator, and I don't like that term, fact canceled, that really should be just simplified. So here, this is the polynomial. This was function, I'm sorry, not polynomial. This is the rational function from the first page for function f, I believe it was. And here I'm just kind of factoring it, and you can kind of see here at this point that I have an x minus 2. Oh, my marker doesn't want to work. There we go. I have an x minus 2 factor in both numerator and the denominator. So recalling about rational functions, the numerator shows you where the roots are and the denominator shows you where the vertical asymptotes are. So essentially, by having a common factor, you're trying to say that I have a solution and a vertical asymptote, something that's undefined at the same point. And that is not possible. So the undefined term wins. There's a vertical asymptote there. And this is what the final simplified function would be. But when the factor simplifies in the numerator and the denominator, that is a discontinuous part of the function, and we would generally refer to that as a whole. So if a factor doesn't simplify, not cancel, if a factor doesn't simplify from the denominator, like this x minus 4 factor is still there, that again shows you where the overall function is undefined, because if I put a positive 4 in for x, I get a 0 in the denominator. So in this case, that would identify where a vertical asymptote is located. Vertical asymptote.
1, 2, 1, 0, 8, 1.
Ignore that. Okay. So now we're going to take a look at working some example problems as far as how can we, when it says analytically, how can we use some math to actually justify what the limit behavior is going to be. And here we're kind of looking at it from a one-sided limit, looking at, this is still that function f, the one that I kind of had written up here. So you can kind of look at it, and I'm going to go ahead and just write out what the simplified expression was, simply because I already have it. I've already factored everything. So this was negative 2 times x plus 3 over x minus 4. Now, of course, we can't do direct substitution with this because clearly if I put a 4 in here, I'm going to get a denominator that has a 0 in it. So we can't do direct substitution, but that one-sided limit, we can get very close to 4. So let's just say that x, for this example, is about 3.99. It's something that's really close to 4, but it's less than 4 because you're approaching it from the left side, so it has to be less than 4. So if I take that 3.99 number in there and I plug it in, I'm going to get negative 2 times 3.99 plus 3 over 3.99 minus 4. Now I'm not actually going to work out the math here. I just know that in the parentheses here I get a positive number and I multiply it by a negative number. Well, positive times negative says that that is going to be a negative number. And the 3.99 minus 4, 4 is bigger, so even though it's going to be a very small number, it's still going to be negative. So I wind up with a ratio that's negative over negative. So negative over negative simplifies to be a positive number. So in this case, I can say the limit of this function as x approaches 4 from the left-hand side, that the limit must approach a positive infinity. And that's exactly what we saw in the graph, but here we're doing it analytically. We're not using a graph now. So here, same thing. This is the same function on the right side. So I'll just go ahead and write the simplified function again. Negative 2x, or parentheses, x plus 3, there we go, over x minus 4. So again, we're going to just kind of take some number that's just, because we're approaching from the right side of the graph, we have to have a number that's going to be bigger than 4. So in this case, I don't know, let's say x is going to be 4.01. So if I take that 4.01 and I plug it into this simplified expression, I'm going to get negative 2 times 4.01 plus 3 over 4.01 plus 4. I'm sorry, minus 4. Now in the numerator, 4.01 plus 3, that's positive. Positive times that negative 2 makes the overall numerator a negative number. And in the denominator, 4.01 minus 4 gives you 0.01 positive, so I have a positive number in the denominator. So negative divided by positive makes the whole thing negative. So that's why it will approach negative infinity in this example. Now, normally what you might do, again, you could take a calculator and just plug those numbers in and actually figure out what the negative number here is and what the negative number here will be. But in this case, we don't actually have to work it all the way through. We can just use a little bit of common sense to see when I'm going to have a positive number or a negative number. So I'm going to encourage you to take a look at these two examples. Go ahead and pause the video now and work out these two examples and see what you get based on the A and B examples that I did. But I'm going to go ahead and presume that you've paused it and done everything that I've asked you to do. So in this case, this particular function, the numerator, doesn't have any real solutions. This is not factorable, so I can't actually simplify anything at all. So I have to pick some number that is going to be, so here we're approaching 1 from the left-hand side, so I have to pick something that's smaller than 1, something that would be to the left of 1 on the number line. So here, let's just say that x is, say, a 0.9. So plugging that in, if I plug 0.9 into the numerator, 0.9 squared is positive. This will give me negative. But here, I don't know. Is it all going to work out to be a positive number or a negative number? So here, you could just go to your calculator, but I've already worked it out in advance. So the numerator is going to be a positive number. And here, 0.9, if you multiply, this is a fraction, so that this is going to get smaller than that 2. So something smaller than 2 minus 2 is going to give me a negative number. So that means this particular function, as the limit approaches 1 from the left-hand side, is that the limit will approach a positive or a negative infinity. And same thing here, we have to approach 1 from the right-hand side. So we have to say, let's just suppose x is equal to a 1.1, something that's to the right of 1 on the number line. And again, if we plug this 1.1 into the function here, we will wind up with a positive number in the numerator. And if I put the 1.1 here, we're going to wind up with something bigger than 2, minus 2. So that'll give me a positive number in the denominator also. Positive over positive says the limit will be positive. So that means as the limit, or the limit of this particular function, as x approaches 1 from the right-hand side, the limit will go towards a positive infinity. That's where we're going to have that vertical asymptote that goes up. Now here, where they're talking about these cases, this is really not much of a stretch as far as where you have, how you justify where there's a vertical asymptote. Essentially, anywhere you have a vertical asymptote, you have to have a 0 in the denominator. So that's exactly what they're showing you here. If x is going to be some number that will produce a 0 in the denominator, like in this example here, coming back to this problem here, if c was a positive 4, then that would give me a 0 in the denominator. It wouldn't matter what's in the numerator, because if I get a 0 in the denominator, the function is undefined. So if x equals c produces a 0 in the denominator, then that means the function is undefined. And it would be the same thing here, 0 over 0. This is actually something that we'll take a look at in a future lesson. This is going to be something that would be referred to as an indeterminate form, but that's something that you would look at when you're trying to take the derivative of something that gives you that. But in this case, we're just trying to justify why as long as there's a 0 in the denominator, whatever that number on the x-axis is, that's going to make the function undefined, telling me that that is where we will have a vertical asymptote. So the limit definition of the identifying where there's a vertical asymptote. So this is what we're going to say. If the limit of some function as x approaches that number from the left-hand side equals either a positive or negative infinity, or the same thing, the limit of some function as x approaches some number on the x-axis from the right side, then the limit will approach, again, either a positive, if it approaches a positive or negative infinity, then, and you can see how we're kind of writing a conditional statement like we did in geometry, then x is equal to c that's where your vertical asymptote is. That's what the equation of the vertical asymptote is, a vertical asymptote. So again, we're coming up on about 12 minutes working out this page, so I'm going to go ahead and pause the video so that they don't get too cumbersome. But we'll pick it up with a separate video again. So thanks for watching, guys, and take care.